Hello everyone, welcome to the study of complex number. Here we are given f of z, where z is a complex number, is equal to 1 over z minus 1. As you can see here clearly, at f of z is not defined at z is equal to 1, because when you substitute this one with 1, you are going to get 0, and the number divided by 0 is not undefined. So we are going to look at singular point in this study. So the point where the function is not defined is referred to as singular point, whereby it does not exist. It is called a singular point. And there are many different types of singular point. There is what is called removable singular point, pose, branch point, and the point on the real axis. So for today's focus, we want to consider removable singular point. Remember, a singular point is a point where the function is not defined. Like in this case here, like in the example you have here, at z is equal to 1, this function is not defined. So let us go to an example 1 of a removable singular point. So we consider function f of z, which is equal to z squared minus 1 divided by z plus 1. So that is the we are considering now. When z is equal to -1, this function is not defined, and the z is equal to -1 is a singular point. So, but this singular point, it can be removed. So what we do, we factorize the numerator so that we get z plus 1 multiplied by z minus 1 divided by z plus 1. Z plus 1, which this and this other part will cancel, and we are going to be left with z minus 1. So here we have f of z is equal to z minus 1. So you can see this one has no singularity, meaning that we have removed our singular point. Now, if f of z is a function defined everywhere except at z is equal to alpha. So f of z is a function which is defined everywhere except at z is equal to alpha, but the limit of f of z as z tends to alpha exists. This is the symbol for exist. Then we say then z is equal to alpha is a removable singularity. It's a removable singularity. I repeat, here if f of z is a function defined everywhere except at z is equal to alpha, and the limit of f of z as z tends to alpha exists, then z is equal to alpha, we call it a removable singularity. So if f of z has a singularity, if f of z has a singularity at z is equal to alpha, remember singularity, it is a point where the function is not defined, then the singularity at f of z, the singularity at z is equal to alpha of f of z is seen to be removable, provided the limit of f of z as z tends to alpha exists. Example, we are to show that f of z is equal to sine of z over z as removable singularity. So here, solution, f of z is equal to sine of z over z. The singularity now, we are talking of z is equal to alpha. Our case alpha is equal to 0. When z is equal to 0, this function here has singularity. But if we take limit of f of z as z tends to 0, which is equal to limit of f of z at z tends to 0, our function is sine of z over z. We can apply L'Hopital's rule here. We differentiate the numerator. So limit, this is the same as limit of cos of z divided by 1 as z tends to 0. This is going to give you 1 because cos of 0 is 1. You can see clearly we have removed the singularity. We have removed the singularity by making use of L'Hopital's rule. We can have another example. A final example in this consideration here, it is this. We are given f of z is equal to z squared minus 1 over z plus 1. So we have to show that, of course, at z is equal to -1 is a singularity, because when you substitute this with the -1, the result will be 0. But now limit as z tends to -1 of z squared minus 1 over z plus 1. This will give you z plus 1 multiplied by z minus 1. I have factorized the numerator, z plus 1, which is equal to limit as z tends to -1 of, so z plus 1 and that will cancel, of z minus 1, which will give you -2. You can see clearly now we have removed the singularity. So thanks so much for taking your time to study with me. For more such videos on singularity of complex numbers, tune on to my YouTube channel so that we may continue learning together. Bye bye. See you in the next presentation.